Welcome back to 3 Deviations. In the last video I said that we were going to focus more on the functions today as opposed to the rules. And that's correct because we'll be covering trigonometric differentiation today, so derivatives of the trig functions. And I bet that a lot of you are fresh out of pre-calc right now, so you probably have a little bit of trigonometry knowledge still in the front of your head, so that will come in handy because we will be using some of those identities. Let's get started. So we're going to start with a graphical intuition of the derivative of the sine function, and after that we're going to prove that intuition rigorously. And after that, what we will do is we're going to use that rigorous derivative of sine to prove the other trigonometric derivatives. And then we'll do some examples after that. So let's start with the graphical intuition. So if I graph sine from -5 to 5, and then I put in some tangent lines, we've got one here with a slope of 1 and one here with a slope of 0, which means that our derivative will have a point there and we'll have a point there. So that means that our derivative looks to be periodic, and it is another trig function, so maybe it's cosine. Well, let's check that rigorously. What we're going to do, we're going to plug this into our old difference quotient that we did a couple videos back. We're going to take the limit as h approaches 0 of sine of x plus h minus sine of x over h. And it should be mentioned that if I write sine of h, do not confuse that with the hyperbolic sine. We're not going to get into that for a while. It's not so it's not going to be the hyperbolic sine. It's just going to be the sine of h. All right. So after this step, we are going to expand because we have an addition in our argument. So we need to use the trigonometric additive identity for sine. So that will be the limit as h approaches 0 of sine of x times cosine of h plus cosine of x times sine of h minus sine of x over h. And we can split this up so that we get the limit as h approaches 0 of sine of x times the cosine of h minus 1 over h plus the limit as h approaches 0 of the cosine of sine of h over h. And this might look weird and kind of arbitrary, but there's a reason I'm doing this, because we have a pair of special limits for these trig functions. And primarily that the limit as h approaches 0 of cosine of h minus 1 over h is equal to 0. That means that this argument just becomes 0. And we also have the limit as h approaches 0 of sine of h over h is equal to 1. So then this one just goes to 1. And if I do that, then that means that this sine of x, this whole limit will cancel out because we're multiplying it by 0. And then there's no, if I multiply cosine by 1, it's just cosine, and this limit has no purpose because there's not even an h. So that means that our derivative just simplifies to cosine. So the derivative of sine of x is cosine of x. Likewise, we can use this strategy to prove that the derivative of cosine of x is negative sine of x. So now we have our first two derivatives. We have the derivative of sine of x, which is cosine of x. And we also have that the derivative of cosine of x is negative sine of x. So we have two trig derivatives that we can use. And now we're going to use this to prove the derivative of tangent. So we're going to take the derivative of tangent, and the derivative of tangent is just sine over cosine. We can take it as the derivative of sine over cosine because the tangent is equal to sine over cosine. So we'll take d dx of sine of x over cosine of x. We'll do this with the quotient rule. F of x will be sine of x, and now that we know the derivative of sine, we can figure out that f prime will be cosine of x. Then g of x is cosine of x, and g prime will be negative sine of x. So now we have everything we can plug into our formula to find the derivative of the tangent. So now we have cosine of x times cosine of x plus sine of x times sine of x over cosine squared of x. If we multiply this out, we get the cosine squared of x plus the sine squared of x over cosine squared of x. And because of the Pythagorean identity, the sine squared of x plus the cosine squared of x is equal to 1. which means that this thing here can become 1, so then we have 1 over cosine squared of x, and because secant is just 1 over cosine, that means that our derivative will be sine squared of x. So the derivative of the tangent is secant squared of x. And again, just like we could for cosine, we can use this to find the derivative of cotangent, which is negative cosecant squared of x. So now we have 2 more derivatives. Finally, we're going to talk about cosecant and secant, and we're going to try to find the derivative of cosecant. And we can just substitute cosecant for 1 over sine of x. And if we put in the quotient rule, f of x will be 1, f prime will be 0, g of x will be sine of x, and g prime will be cosine of x. Now we're going to plug this into our rule, that is sine of x times 0 minus 1 times cosine of x over sine of x times sine of x. And that will just become negative cosine of x over sine squared of x. We can split this function up to become negative cosine of x over sine of x times 1 over sine of x, which will just be the negative cotangent of x times the cosecant of x. So now we have our derivative. The derivative of cosecant of x is negative cotangent of x times the cosecant of x. Likewise, we can do this for secant, and we will find that the derivative of secant of x is just tangent of x times secant of x. So now we have all 6 derivatives for our trig functions. We know that the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, the derivative of cosecant is negative cotangent cosecant, the derivative of secant is tangent secant, and the derivative of cotangent is negative cosecant squared. All right, so now we have everything we need. So now let's do some examples. So just to make sure we didn't forget anything, we're going to take the derivative of all of these functions. We're going to take the derivative of sine of x plus cosine of x plus tangent of x plus cosecant of x plus secant of x plus cotangent of x. And if you remember what we saw in the last slide, the derivative of sine of x is cosine, then minus sine of x plus secant squared of x minus cotangent x times cosecant x plus tangent of x times secant of x minus cosecant squared of x. That was our first example. Let's do another. All right, so we are going to take the derivative of x squared times the sine of x. This is going to require us to use the product rule. We're going to pick f and g. X squared will be f, and sine of x will be g. And f of x is x squared. F prime will be 2x through the power rule, and then g of x will be sine of x, and g prime through the derivative of sine will be cosine of x. Now we can plug this in. We will get 2x times the sine of x plus x squared times the cosine of x. And we cannot simplify that any farther, so that is our derivative. Now let's do a word problem. This one's going to involve some harmonic motion. Maybe you're aware of this from physics. If not, it's fine. I'll explain some of it as well. So, an object at the end of a spring is stretched 4 inches beyond its equilibrium and released at t equals 0 with the position function of x of t equals 4 cosine t. Find v of t and a of t. Now we've seen this before, and the only difference is that we're taking the derivative of a trig function. And if I want to draw this out, we're going to have our spring here, and then we'll have our mass here, and we'll have our equilibrium will be here. This is where the spring will just rest, and we're stretching it 4 inches beyond its equilibrium. So if I want to find v of t, I'm going to take the derivative of the position function, so the derivative of 4 cosine t. And we do not need to apply the product rule. We can just separate that 4 out and take the derivative of cosine of t with respect to t, and that will be negative 4 sine of t. If we want to find acceleration, we're going to take the second derivative of 4 cosine t, and that will just be 4 times the second derivative of cosine t, which is negative 4 cosine t. So now we have a solution for a word problem. And it should be mentioned that you might be seeing, hey, I can take all these antiderivatives here with these trig functions, and these trig functions are what we call infinitely differentiable, because if we keep taking the derivative of sine, it's just going to repeat. It's just going to keep going between sine, cosine, negative sine, and negative cosine. So we can take as many derivatives of sine and cosine as we want. And this doesn't happen with our polynomials, because at some point with our polynomials, we will run out of powers. So that's something that's pretty cool about these trig functions. All right, that is it for trigonometric differentiation. Please like and subscribe. We will see you guys later. Thank you for watching.